Welcome to the lair of the Batty Boffin.
Hi there Batty fans, time for a little bit more electricity with the Batty Boffin. Now, in earlier videos we've been doing some calculations with the voltage, the resistance and the current using these formula triangles around a little circuit diagram. And we've just got an interesting one here today. Here's my circuit diagram and here it is on my handy dandy little clip circuit things. It's very similar to the one we've been doing before, except that I've taken out the light. Because before, remember, we switched this on, we had the light, we calculated the voltage over it and all that kind of thing. I haven't actually got a light on here. In fact, there's nothing in this circuit at all. We've got the batteries pushing out the electricity, the switch, which is currently open, like that, meaning there's no electricity going through. And there's nothing in here to use up the electricity. Basically, this has got a resistance of nothing in here. What happens when we do it in here, put it in here? So we've got 6 volts worth of electricity. Okay, so V is 6. Resistance is 0. So 6 volts and 0 ohms. So, something for you to try. Put those into our formula. We're wanting to calculate I. So remember, on these formula triangles, you cover up the thing you want and what's left is the formula for it. And see if you can work out what happens to I. You might get a weird answer. So pause the video, have a go at that now, please. Right, we're going to use the formula I equals V over R from our formula triangle. So we're going to put 6 divided by 0. 6 divided by 0, not 0 divided by 6. 6 divided by 0. If you did that on a calculator, you probably got an error because the answer is infinity. It's a divide by 0 error. You can't do it. This is in fact what's called a short circuit. The electricity, if I switch this on, I am not going to switch this on. I'm leaving it switched off. If I switched that on, then the electricity would come straight round here and it would go so fast that the current would actually get incredibly high and it would actually start to heat these up and it might actually start burning some bits on here. It might start, burning some of the bits of the plastic on it. And it would drain the batteries very, very quickly and actually be quite a dangerous thing. Short circuits are quite dangerous things, so you should never, ever build a circuit that looks like that. You always must have something in it that is a resistance. And in order to stop things like this happening, we actually have safety devices built into the vast majority of all electrical things, heaters and kettles and everything, motors, they all have things built into them. Something that looks remarkably like that, that's a resistor. Something that's very, very similar has a symbol that looks like that, and it's a fuse. And a fuse is something that's designed to stop a short circuit. So what I should have in here is a fuse, so that if I accidentally switched that on, the current would start charging around here really, really fast. And what a fuse does is when the current gets more than a certain amount, the fuse breaks. It's designed to break. And effectively, if that was a fuse in there, it would just break the circuit. Oops, there we go. So my fuse would just break and break the circuit, effectively switching it off. So fuses are bits of a circuit that are designed to break when the amps get more than a certain amount. Now, if you've ever come across fuses, you'll know they're actually rated in amps. You get 3 amp fuses and 5 amp fuses and 13 amp fuses. So those are for different amounts of amperage, different amounts of current going through. So we're going to do some calculations with that just now. Go and get yourself a cup of coffee. I've got mine here. And come back in a minute when I've wiped down the board and we'll do some calculations all about fuses. So here are some practical calculations that we can do with the things around us every day. The kettle that I use to make my cup of coffee has got a label on it, like this. Most of the electrical products around your house will have this. Mine says 240 volts. It actually says 230, 240, but I'm going to use 240 because it makes the calculations easier. Other countries might have things like 110 there. It's also got this 3000W. What's that? Well, yes, actually, watts. That, watts. It's a joke. It's watts. That's volts and that's watts. Watts. Those are the unit of power, named after Mr. James Watt, who I believe was a Scottish chap. Very clever. So, my kettle uses electricity at 240 volts and it uses 3000 watts of power to make it go. That's quite a lot. Sometimes in watts we refer to kilowatts, which means thousands of watts, like, kilometers and kilograms. So that is 3 kilowatts, 3000 watts or 3 kilowatts. That's the power consumption of my kettle. Well, you say that's great, but we've used volts, current and resistance. How do we get current out of that? Well, it just so happened that the power that an electrical thing uses is equal to the voltage times the current. That is, it's how hard the electricity is going round and how fast it's going round. Current, remember, is how fast it's going round, and voltage is the amount of oomph behind it. So if you do oomph times running past, you get power. Handy dandy little formula triangle here. Power equals the volts times the current. Now we've got the volts and we've got the power. That means we can calculate the current. So it's time for you to pause the video and have a go at doing that now, please. Right, let's work through that together. In our case, the power was 3000 watts and the voltage was 240. We know from our formula triangle, if we cover up the thing we want, what's left is the formula. It's P divided by V. So the current is equal to the power divided by the voltage. Or I'll just do it down here, and I'm going to do that in a different pen because that one's kind of running out a bit. Green. I is equal to 3000, that's my power, divided by the voltage, 240. Right, 3000 divided by 240, that's the same as 300 divided by 24. Those both cancel by 3, so that's 100 divided by 8. 100 divided by 8 is 12.5. You can halve it, then halve it, then halve it. So that's 100, halve it 50, halve it 25, halve it 12.5. 12.5 amps. 12.5 amps. Well, that's very good because we have fuses in Britain and they come at 3 amps, 5 amps and 13 amps. So I'm going to use a 13 amp fuse to protect that. So in the plug of my kettle is a 13 amp fuse. Now this is something you can do. Have a look around all the things in your house. Look at, I know, a CD player, look in a lamp, look in a toaster. Well, not in them, look on the bottom. You're looking for a little plaque like that somewhere. It'll have the voltage, it'll have the power consumption in watts. Things that are involved in heating, like heaters and irons and things like that, tend to have quite large wattages there. Other things tend to have much lower ones. CD players will be a lot lower than that. And you can put the power and the voltage into this formula triangle, calculate the current, and from that work out what size fuse you need. Okay, so have fun with that, and I'll see you next time, Batty fans.